Hey folks, in this lesson I'm going to go over the 5 different kinds of reactions that you need to know for this course, classifying the different kinds of chemical reactions. We'll talk about how you predict the products from a chemical reaction given the reactants and knowing the different kinds of reactions. And it will also be a bit of a review of the previous lesson that I put together for you, which was on the balancing of chemical reactions. So the first of the reaction types that you need to know, formation reaction or simple composition reaction, also referred to as synthesis reactions. What you're doing is combining elements together, forming a bond and a compound in the process. So the two elements you're going to have joining together. They could be single atoms on their own, like a silver atom, or they could be those molecular elements as well that are diatomic, like nitrogen or chlorine or oxygen. So I'll give you one of each in the first one here, and in fact I'll just kind of show you in generic terms. So if I just use letters A, B, C, and D to represent any of the elements from the periodic table, we're talking about one element that I'll just call A, and forming a bond with another one that I'll call B. So when you form that bond and join them together, you have a compound that will now have these two that are attached together. So we'll go over a few examples of each one of these as well. So for the first element, why don't we just make it one of the metals? And let's say that it is iron. Remember that iron is one of these multivalent transition metals. It can have two different possible charges, so it would have to be specified which one. In this case here, it's going to be the iron 3 that I'm going to use, and we're going to react that with oxygen. Remember, oxygen, when you're told oxygen, it is always diatomic. O2, that's going to be a gas. So these are two elements, and I'm just going to combine them together. So this would be our A and our B. We're going to form a bond between them. We have a metal and we have a non-metal. So that means it is going to be an ionic compound that is forming. Make sure you're writing a correct ionic compound. So what would that be if you join these together? Well, I mentioned that we're going to use the 3 plus for the iron. Oxide is always 2 minus. As we've talked about before, of course, cross those. The point is you can have no charge in your compound that you're forming. You have to have an equal number of negative and positive charges. So we bring our Fe, remember always write your metal first, your non-metal second, crisscrossing. That means that we should have a 2 on the iron, and we would have a 3 on the oxygen. So that is our prediction of what we're going to get for our product, and this is our simple composition, formation, or synthesis reaction. Now balancing, this may or may not be balanced. You always need to check, and if it's not balanced, then you need to go ahead and put coefficients in front in order to balance it. What we have on the left-hand side, iron and oxygen, of course, is exactly what we should have on the right-hand side as well, and we do iron and oxygen, so we can have the conservation of matter. We need to have the same atoms, and we need to make sure we have the same number of each as well. So let's count them up. On the left-hand side, which of course is the reactant side, we have 1 iron to do our little bit of a tally here. Again, the 2 after the oxygen means we have 2 of them. So the 2 are actually attached together to oxygen. On our right-hand product side, what do we have? 2 after the Fe tells us that we have 2 iron, 3 after the oxygen. We have 3 oxygen. So of course it's not balanced because we don't have the same number on either side of the reaction arrow. Leave oxygen until last is what we talked about with the balancing. That leaves us with only iron that we're going to start with here. And again, the only way that we can balance it, I cannot put a 2 after the iron. I can't make it Fe2. I can only put numbers in front. As soon as you put a number in front, it applies to that element. If there's more than one element in that compound, it applies to everything after that as well. I have 2 iron on the right. I need 2 on the left, so I'm going to put a 2 in front of the Fe. Now I have 2. I don't have the oxygen balanced. So take a look at what is the lowest common denominator of these two, and it is 6. So that's what I'm going to try to get on each side, which means I have to put a 3 in front of the oxygen, O2, on the left. Now I have 3 times 2, or 6. And on the right, I'm going to put a 2 because 2 times 3, again, is 6. So now I balanced my oxygen, but of course by putting in 2 in front of the Fe2O3, I no longer have the iron balance. So now I have 2 times 2, 4 iron on the right. I need to get 4 on the left. So I'm going to change this 2 to a 4 for the coefficient. And now I have 4 on the left as well. Always double check. 4 iron on the left, 2 times 2, 4 iron on the right. 3 times 2, 6 oxygen on the left, 2 times 3, 6 oxygen on the right. This is a balanced reaction, and this is a simple composition synthesis or formation reaction. Let's go ahead and take a look at another one of these. Doesn't have to be ionic, it could be molecular as well. In this case, it wouldn't be so much predicting, you would have to be told what they actually are. So we could have P4 phosphorus, which as we know is solid. We could have Cl2 diatomic, which is a gas, and we could form PCl3, which ends up being a liquid. So you would have to be told this because again there are different ratios that we can have for molecular compounds, and this is phosphorus trichloride that we would have on the right hand side. But we can go ahead and we can still balance this, so let's just kind of do that quickly. We only have phosphorus and the chlorine on both sides. Let's start with the phosphorus because that's what we have the highest number of. So if we have 4 on the left, we want to have 4 on the right. Put a coefficient in front of the phosphorus trichloride. Now if we take a look at the chloride or chlorine on the right, we have 4 times 3, 12. We just need 12 on the left, so we need to put a 6 in front. 6 times 2 would then give us 12. Let's just do one more of the ionic ones. Let's take another metal here, Ca solid, calcium solid, and let's combine that with Br, which is bromine. Bromine is one of those in group number 17, which is diatomic, and it's also a liquid at room temperature. Combine these together and we end up with calcium bromide. Again, let's just double check, make sure we have the right formula here. It is Ca2 plus Br1 minus. Crisscross those charges, so we should have a 2 on the Br. Again, formation reaction. This is an element. This is an element. We combine them together to form our compound, forming a bond between the two of them. In this case, you might notice that it's actually balanced already, so you don't need to add any coefficients in front. What that means is that each number in front is a 1 that we do have. That is already balanced. The next kind of reaction is really just the reverse. So instead of combining two things, we're going to split them apart. So we're going to start with our compound in generic terms, AB, and we're just going to tear it apart into the elements A plus B. Simple decomposition. Let's do this one here. Let's take sodium nitride. This one ends up being a solid, and we're just going to tear it apart. When we tear it apart, we end up with the sodium, which is a metal, ends up being solid, and we end up with nitrogen N2 diatomic. Nitrogen is diatomic, and that is a gas. Okay, so we're just tearing apart our compound into the elements. Let's do our balancing again, step by step, at least for the first few here. Sodium and nitrogen. Sodium and nitrogen. Maybe check at the beginning, it might be balanced from the start. This one of course isn't, because we have the same number of sodium on either side, but we don't have the same number of nitrogen. Lowest common denominator is 6. Try to get 6 on either side. So we're going to put a 2 in front of the sodium nitride, 2 times 3. Now we have 6 nitrogen. We want to get 6 on the right-hand side as well, so we're going to put a 3 in front of the nitrogen gas. 3 times 2 gives us 6. Now we kind of messed it up a little bit for the sodium. We have 2 on the left-hand side, so we need 2 on the right-hand side. So simply putting a 2 in front of the sodium is going to fix that. Let's do one more. For the simple decomposition, let's make this a really kind of easy one. Let's just take water. H2O, could be liquid or gas, or solid for that matter. Here I'm going to write it as a gas. We're going to take that and split it apart into its elements, which is hydrogen diatomic gas and oxygen diatomic gas. So hopefully, again, you realize that if you are getting the formula wrong, your balancing will most definitely be wrong as well. So always kind of double check that. Make sure you have it correct before you try and go ahead and do your balancing. Let's try and speed it up here a little bit. So H2O, we have 2 hydrogen on the left, 2 on the right. We have 1 oxygen on the left, 2 on the right. So we need to put a 2 in front. Now we have 2 oxygen on the left and 2 on the right. But now we have 2 times 2, 4 hydrogen on the left, so we need 4 on the right, so we just stick a 2 in front, and that's going to balance our decomposition reaction. So now we're going to go on to the single replacement and double replacement reactions. So for these ones here, you're going to do exactly the same as what we just did, identifying the reaction type, just like we did for the simple composition and decomposition, using the rules for ionic molecular predicting the compounds. That's just what we did as well. Some of the molecular formulas, yeah, you do need to remember, like water even, you need to remember that. Use the solubility table. I haven't jumped back and forth between that, but you need to use the solubility table. And in the end, we're looking for the simplest whole number coefficients in order to balance it. So that will also apply to the single and the double replacement. So what's going on here? Single replacement, you're exchanging metal for metal, or not quite as common, but it might also be non-metal for non-metal. You cannot exchange a metal for a non-metal. So what's going on? Well, we start with an element, which generic terms I'll call A, and we're combining it together with a compound. And we'll call this BC. So if these ones here are both metals, we're just going to flip them around. Okay, both A and B are metals, and I'm just going to exchange them. So now we're going to have A, that's with C, the nonmetal, and it's B that's going to end up on its own. So that is if we have A and B are metals. But it is possible that A is not a metal. So let me just grab a different color here. So it's possible that we could have A plus B and C. But now we're going to flip around these two here, and those are the nonmetals. So what you have on your own is not a metal, it's a nonmetal. So now what we're going to get is going to be C on its own and B and A together. But B is the metal, right? So we need to write that first, B and then A. And here we have A and C are nonmetals. So if A is a nonmetal, I can only switch it around with the other nonmetal. So yeah, that's what it says down here. Metal replaces a metal, nonmetal replaces a nonmetal. That's the only possibility. Just like we did before, for composition and decomposition. Complex or polyatomic ions, we've come across these before with balancine. Keep them together if they appear on either side of the reaction arrow. If you do have water, sometimes it's easier to write it in the form of HOH rather than H2O. So a couple of examples here. First of all, for the single replacement reaction. Okay, single replacement is what we'll take a look at, and then I'll talk about and do the double replacement as well. So we're going to have an element on its own. Let's make it, I'll write it up above here, aluminum. Aluminum is a metal, solid. And for this one here, I'm going to react it with sulfuric acid, H2SO4. And that one's going to be AQ because it is an acid. So here, aluminum is a metal. Hydrogen is acting as the metal, so it's those ones that I'm going to flip around. So what does that mean? Hydrogen is going to end up on its own, but hydrogen is always diatomic. H2, which is the gas. Now I'm going to have aluminum, which is with the sulfate. Now be careful here. Aluminum is 3+. And the sulfate, you need to take a look at your table of polyatomic ions. And the sulfate is the SO4 2-. 2-. Crisscross the charges. So our compound that you would now predict on the product side is going to be Al2. We need brackets here. SO4, and outside of the brackets is the 3 that was on the aluminum. And this one here actually ends up being solid for the state. Balancing, a little bit more difficult. We have aluminum, we have hydrogen, polyatomic ion, keep them all together. We have SO4 on both the left and the right hand side, don't split them up. On the right then we have aluminum, we have hydrogen, and the SO4. So coefficients. Let's grab a different color here. Coefficients that we can stick in front, or maybe it's balanced. It's not. Take a look at the aluminum. You have 2 on the right, 1 on the left. It's not balanced. So let's tally it up. On the right-hand side, we have left-hand side, we have 1 aluminum. We have 2 hydrogen, and we only have 1 sulfate. Right-hand side, we have 2 aluminum. We have 2 hydrogen, and we have 3 SO4s. So a little bit of work to do here. Let's start with the one that we have the biggest number of, and that's the sulfate, and let's try and fix that one first. So if we have 3 over on the right, we need to get 3 on the left. We can't put a 3 after the SO4, but we can put a coefficient of 3 in front of the sulfuric acid. That means that we now have 3 sulfate as well, but we also have 3 times 2 hydrogen, because that 3 applies to not just the sulfate, but the hydrogen. 3 times 2 is 6 hydrogen on the left. We need 6 on the right. We have 2, coefficient of 3 in front. 3 times 2 is 6, and we're okay with that. The last one is aluminum. We have 2 aluminum on the right. We just need to put a 2 in front to get our 2 aluminum on the left. Let's double check. 2 aluminum on the left, 2 aluminum on the right. 3 times 2, 6 hydrogen on the left. 3 times 2, 6 hydrogen on the right. 3 sulfate on the left, 3 sulfate on the right. This is a balanced reaction for single replacement. Let's do one more of these single replacement reactions here. Well, at least one more. Maybe I'll make this one a little bit easier. I won't use one of the polyatomic ones. Let's take magnesium metal, and we're going to react that with nickel chloride. This is nickel 2 NaCl, and this one's going to have to be AQ or aqueous. And we're going to go ahead and write our products. Magnesium and nickel are the metals, so we're going to flip those around. Nickel is now going to end up on its own, and we're going to have our magnesium 2 plus. Now with our chloride 1 minus, crisscross, and we end up with MgCl2 for this one, and that ends up being AQ. Balancing, how does it look? 1 magnesium on the left, 1 on the right, 1 nickel on the left, 1 on the right, 2 chloride on the left, 2 on the right. It is already balanced. All the numbers in front have a coefficient of 1. It is already balanced. You don't need to stick any other numbers in front here. One more. That one was kind of quick, so let's do one more. Let's do copper, Cu, copper, metal. React that with silver, which is 1 plus NO3, AQ, metal, exchange with the metal. Silver's going to end up on its own. And we're going to have CuNO3. And this one here. So for the copper, we could have two different possibilities. It could be the 1 plus or it could be the 2 plus. I'm going to make this the 2 plus, which means I would need brackets here and put a 2 on the outside just to make it a little bit more interesting. So I'm saying Cu2 plus NO3 minus is what we're using to form our compound that we do have here. Okay, so when we do that, take a look at our nitrates, take a look at our copper, our silver. That's what we have. Don't split up your nitrate polyatomic ion. We have copper, we have silver, and we have our NO3 1 minus, which is our nitrate. Oh, sorry, that one's, yes, it is the nitrate. NO2 is the nitrite. Same thing on the other side. Cu, Ag, NO3. What do we have for numbers? 1, 1, 1. Over here, 1, 1. This one is not balanced. NO3, stick a 2 in front of our silver nitrate, and that will, at least for now, balance the nitrate. Give us a 2 here. But now we have 2 silver. We need 2 more on the other side, put a 2 in front, and now that should be good as well. Double checking, 1 copper on the left, 1 copper on the right, 2 silver on the left, 2 silver on the right, 2 nitrate on the left, 2 nitrate on the right. We have a balanced reaction. Single replacement were those ones. Double replacement, in some ways, these are even easier, although you do have 2 different compounds that you're reacting together. Here, same thing. You're just switching around the metals and the non-metals. But there's no confusion in terms of what is the metal and what is the non-metal and kind of mixing that up, or at least not as much confusion. So these 2 are attached together. A and B, that's our first compound, first reactant. C and D are attached together. They're our second compound. What are we going to do? Well, if these are both ionic compounds, we're just going to flip around the metals. That's really it. So now we're going to have A with D. C is the metal, so we need to write that first. C with B in generic terms. Ions are exchanged between the 2 compounds. Let's take a look at a couple examples of this one here as well. So let's start with potassium carbonate. C2, CO3, CO3 2 minus. That is the polyatomic ion, carbonate. And let's do magnesium bromide. Again, if you're given the word equation and if you get these wrong, then everything will be wrong for your balancing and for probably predicting your products as well. What are we doing here? We're just flipping around the metals. So now we're going to have magnesium, which is Mg2 plus, with carbonate, which is CO3 2 minus. crisscross the twos, but they're going to cancel out anyway, so we don't need brackets. MgCO3 is one of our products. And the other one, we're now going to have the potassium with the bromide. It's not balanced. We have potassium, we have carbonate. So a little bit more to write down here. We have 4 different elements or polyatomic that we do have. Br, same thing, of course, hopefully on the other side, or everything again is going to be wrong. That's what we have. Let's do our quick tallies. 2 potassium, 1 carbonate, 1 magnesium, 2 of the bromide. Potassium, we have 1, carbonate, we have 1, magnesium, we have 1, and bromide, we have 1. It's just, well, the potassium and the bromide. So let's fix the potassium first of all here. Put a 2 in front. That means we have a 2 here. Oh, we also have a 2 here. And now it's all good. It is balanced just by doing that. Let's do one more, bumping it up a little bit. So we have, let's make this one with a couple of polyatomic ions in both of our reactant compounds that we're starting with in the first place. Let's pick Pb, which is lead, lead 2 nitrate. I'm going to go back and show this again just to make sure everyone is clear with, again, writing the formulas. Lead 2 is Pb2 plus, nitrate is NO3 1 minus, and that's why the 2 needs to go outside the nitrate and in the brackets. This one here is probably, well, it is dissolved in water, it's AQ, and it's also dissolved in an acid, and that acid is H2SO4. So 2 polyatomic ions. We have the nitrate and we have the sulfate. This one is an acid, so it's AQ, that is sulfuric acid. What are we switching around? Well, our hydrogen is acting as the metal, so we're flipping that around with our lead. So now we're going to end up with our lead, Pb2 plus, SO4 2 minus, crisscross, the 2's will cancel out, we don't need brackets, PbSO4 is what we're going to get for one of our species as the products, and AQ, and our other one is going to be another acid, which is going to be our nitric acid, HNO3 AQ. Okay, so I predicted the products just by flipping around the metals. Always have to double check to make sure you have the right formula. Now we can go on to the balancing. Maybe I won't write everything down. We'll see if we can do it without writing everything down, just kind of taking a look at it. It's not balanced already because we can see that there are 2 hydrogens on the left and only 1 on the right. And same thing with the nitrate. Let's start with the nitrate. We have 2 on the left. I'm going to put a 2 in front here, which gives me 2 on the right. I've doubled up the hydrogen. Oh, and now I have 2 on the left as well. Okay, let's just check. 1 lead, 2 nitrate, 2 nitrate, 2 hydrogen, 2 nitrogen, or hydrogen, 2 sulfate, or sorry, 1 sulfate, and 1 sulfate. We're good. That one is balanced. So now we have decomposition, we have formation, we have single replacement, we have double replacement. We just have one more to go, and those are combustion reactions. So here we have a compound, and it's always going to be oxygen. And then I just have here most common oxides, but most of the time for us, the products are always going to be the same 2 things, and that is carbon dioxide and water. That will be the case if your compound is what's called a hydrocarbon or an alcohol, where you do have carbons and you have hydrogens and maybe you have oxygens in there as well. So yeah, most common oxides, if it is in a hydrocarbon, then it will be carbon dioxide. If you have nitrogen oxides or sulfur dioxides, those might be produced as some of the oxides as well. If in your compound you have nitrogen or sulfur as the elements. Water is produced in the gas state for these combustion reactions because it is at high temperature. So let's take a look at a couple of examples here. Do the balancing. A little bit of a trick with this as well, and this is really where leaving oxygen till last, hydrogen until second last does become kind of important. So I'm going to show you the ones that are using carbon. So the products will always be the same, carbon dioxide and water. So the first one here, we're going to do C2H4, which is ethene, and we're going to react it with oxygen. So if you do have a hydrocarbon combustion, this is carbon and hydrogen, this is a hydrocarbon combustion, it's always going to be oxygen, that has to be the other reactant, and it's always going to be CO2 and water that are produced. So these three here, if you're burning something that has carbon and hydrogen or carbon, hydrogen, and oxygen, this will always be the same. There will just be different coefficients in front. So what are those coefficients? Well, we need to do our balancing. We need to do our tally. Let's go back to writing everything down. We have carbon, we have hydrogen, we have oxygen. Over here, we have carbon, we have hydrogen, we have oxygen. Carbons, we have 2 on the left. We have 4 on the left for hydrogen. We have 2 for oxygen. On our reactant side, on our product side, we have 1 carbon. We have 2 hydrogen. Be extra careful with the oxygen because they are here and here. 2 plus another 1. 3 oxygen. Leave the oxygen until last, leave the hydrogen until second last, which means, well, we have one thing to start with, and that is our carbon. Let's fix it. We have 2 on the left, we need 2 on the right. Let's put that coefficient in front, and now we're good. We changed the oxygen, but we're going to leave that until last anyway. Hydrogen, we have 4 on the left, we have only 2 on the right. We need to put a 2 in front here. 2 times 4 gives us 4. Now that's balanced. Let's take a look at our oxygen. We have 2 plus or times 2. We have 4 oxygen that are coming from the carbon dioxide. And we have 2 that are coming from the water. So we have 6 oxygen in total. We need to get that on the left. So if we put a 3 in front for the coefficient, 3 times 2 gives us 6. Just one more reminder, there is no number in here, but it does mean 1 if there is no number. Just one more that'll add in the final little bit of a twist for combustion reactions. This one here I'm going to use ethanol, C2H5OH. This is an alcohol, and it is the alcohol that you find in alcoholic beverages. It burns. When it burns, of course, it needs oxygen to burn. Gas, this is liquid. Alcohol is a liquid. What do you get as your products? The same as in the previous reaction, CO2 and H2O. So whenever you have a hydrocarbon combustion reaction or one that has oxygen, these will always be your products. Both of them are going to be a gas because it is at high temperature. Let's take a look at our numbers. We have carbon, hydrogen, and oxygen. And this is the order that we're going to try and balance them in. Carbon, we have 2. Hydrogen, again, tricky because it's here. We have 5. And then you have another one, 6. Oxygen, we have 2 to start off with. Carbon, we have 1. Hydrogen, we have 2. Oxygen, 2 here. 1 over here. We have 3. Start with carbon. Put your coefficient in front in order to balance your carbon. Put a 2 in here. Now we're good with that. Let's not worry about the oxygen yet. Let's do the hydrogen. Hydrogen, we have 6 on the left. We need 6 on the right, so let's put a 3 in front of the water. 3 times 2, 6. Now we're good with that. Now here it's the water that's kind of tricky, or sorry, not the water, but the oxygen. So here, how many oxygen do I have? 2 times 2. I have 4 oxygen in the carbon dioxide with the 2 coefficient in front, plus 3 equals 7. This is an odd number. This is where you get to use a fraction. So if for your oxygen on your product side you have an odd number, this is what you get to do. You get to use that odd number, put it in front of the oxygen, over 2. So think of it this way. Now we have 7 times 2 divided by 2. We now have 7 oxygen on the left, and that's exactly what we have on the right. So we do this with oxygen for combustion reactions. We don't do it with very much of anything else, but it's here that yes, you can write a fraction. And when you write the fraction, it's always because the oxygen on the right-hand side, it is an odd number.